Good morning, class, and welcome to this lesson on Magnetism 5, torque on a loop of wire. Today, we will be able to identify which way a loop will rotate due to the torque provided by the force of a magnetic field. Okay? So far we know, this is going to be a review right here. So far we know that if there is a current in the wire, there and this wire is in a magnetic field, there will be a force provided by that magnetic field. Okay, there's going to be a force provided by that magnetic field, and that force, just as a review, is equal to the current times the length of wire times the magnetic field times the sine of theta. Okay, so we know that a force will be provided when a current is in a wire. Okay, so what if we have a loop of wire? What if we have a loop of wire? So here is a loop. Okay, here is a loop, and we're going to send a current through this loop here. We're going to send a current through this loop. Well, with these types of problems, it just requires a little bit of perceptual ability, and this is going to be difficult for me to explain because I have a 2D board and this is a 3D concept, but I'll try my best. Let's think about the right-hand rule in this situation. And I'm going to start off with the current starting here, and it's going in this direction. Okay, it's going in this direction. Okay, and I'm going to start off looking at this top piece right here. Let's start looking at that top piece right there. Well, if we do the right-hand rule on this, and I suggest you do this as I'm saying it, the current right here is facing to the right. It's facing to the right. So we're going to stick our fingers to the right this way. Okay, down this shaft right here. Well, the current's going this way, which would be our thumb. Our thumb will be pointing that way, and the magnetic field. Notice here the magnetic field. So this is current, and the magnetic field are both going in the same direction. They're both going in the same direction. So in this situation, F equals ILB sine theta. This is going to be the sine of 0. The sine of 0 degrees, because there's a 0 degree difference between these two. So the force on this top section right here is 0. So that side will not provide any current. And that is typically a multiple choice question that you might receive on some sort of test. Okay, that they're going to try to trick you and say which parts of this loop is going to have a current provided, and you should know that this loop has no current because the angle between the magnetic field and the current is the same. However, we're going to check out, I'll change colors. We're going to check out section 1 and section 2 now. Section 1 and section 2. And this picture right here is a top-down view, so we're looking down on top of this to look at these two. Okay? So, the current's going up right here. So that would be our thumb. Our thumb is pointed in the up direction. The magnetic field is going to the right. So your fingers are going to the right this way. So your thumb is pointed up and your fingers are pointed to the right. Which way is your palm facing right now? Your palm should be facing the screen that you're looking at, or it's facing into the board. So the force is going into the board, and that's this way right here. Okay? And then if you take your thumb on this section right now, the current's now going down. So our thumb is going to go down. Our fingers are going to the right, the magnetic field. Our palm is now facing us. So now the magnetic field is pointing out of the board, or the magnetic force is pointing out of the board, excuse me. So we have a force pushing it into the board on this side and out of the board on this side. So as we can tell, if we look down on it like this, it's going to rotate in this direction or in a clockwise direction. For the purposes of AP Physics, that's really all you have to know for this. You have to be able to look at a picture, do the right-hand rule to both sides, and figure out which way it's going to rotate. Okay? And that's pretty much it. Some questions will just give you some magnets and it'll have north and south, but it won't have the field lines. You should know that magnetic field lines go from north to south. That's something that you should be able to intuitively know based off our prior discussions. Okay, and the current may or may not be given to you. Okay, so you need to be able to look at a picture and determine if it's going clockwise or counterclockwise. Now, I'm going to show you one more. This is the same picture, okay? This is the same picture. Notice we have the same magnetic field, we have the same current. When this picture is associated with this picture right here, okay? It is perpendicular. The current is perpendicular, or the the loop of wire is kind of facing flat, straight on with the north and south here, okay? This is where we're going to get maximum torque. This is where we're going to get maximum torque. Why? Because it's a 90-degree angle. It's a 90-degree angle between the force and the lever arm. The force and the lever arm. And as you might remember, torque is equal to the lever arm, the force times the lever arm times the sine of theta. So the sine of 90 is equal to 1. And so this is where at 90 degrees here is where we're going to get the most torque, or the maximum torque, which is also a typical test question. Where is this thing going to spin the most? At this point right here, here is the top-down view of this picture right here when the loop is facing, when it is facing it head on, not sideways like this one, but head on like this way. If we do the right-hand rule for each side, you can see the force is pointing directly out. The force is pointing directly out. So there's actually no torque here. So in this position right here, there is actually nothing, there is no force trying to cause it to rotate. There is no force, no torque trying to cause it to rotate. But the reality is here, this will continue to rotate. Why? Because the force provided in this section right here will carry out through this one, and this loop will have some inertia, and its inertia will carry it forward. It'll keep rotating until it hits this position again, and it'll continue to go. So just as a little prequel here, this is an example. Of what we would call a motor. We have electrical energy. Being converted. We have electrical energy being converted into mechanical energy. So just imagine if this shaft here was connected to, say, wheels, and so it's causing the wheels to spin like in a car. Okay, so we have electrical energy from the battery and a magnet causing a loop to rotate. This loop is attached to something which, for example, makes wheels turn. This is where we get a lot of DC motors from in like little RC cars and stuff. This is how they work. Electrical energy gets converted into mechanical energy when we have a current and a magnetic field. Okay, so once again, just to recap, with this topic in my class, all you have to do is really know which direction it'll rotate, and we'll practice more of these in class.